December 2025. A team running a Dell PowerEdge server announces a new world record. They've computed pi, not to a few digits, not to 1,000 digits, to 314 trillion digits. If you printed those digits at standard size, the page would stretch from Earth past Pluto and keep going. The computation took months. The disks alone weighed more than a person. But here's the strange part. The algorithm they used to do it isn't new. It was published in 1989 by two brothers working out of a cramped apartment in Manhattan on a homemade supercomputer they'd welded together from spare parts. It's called the Chudnovsky algorithm, and every single pi record set since 1989, every one, has used it. That's nearly 40 years of unbroken dominance. So today we're going to look at exactly what it is, why it's so absurdly fast, and how a one-line formula ended up being the most efficient way humans have ever found to compute pi. Let me put the speed in perspective. Archimedes, around 250 BC, used polygons inscribed in a circle. He got pi to about 3 digits. That took a lifetime of geometry. Madhava in 14th century India found an infinite series pi over 4 equals 1 minus a third plus a fifth minus a seventh, and so on. Beautiful formula, but to get just 10 digits of pi from it, you'd need to add up roughly 10 billion terms. It's correct, but it's painfully slow. Newton in 1666 cooked up a much sharper series and got 15 digits. Machine's formula, 1706, pushed past 100. Ramanujan in 1914 dropped a bombshell, a series where each new term added about 8 correct digits to your answer. 8 digits per term. That's astronomical compared to Madhava. Then in 1989, the Chudnovsky brothers improved on Ramanujan's idea. Their series adds about 14.18 correct digits of pi for every single term you compute, per term. To get 1,000,000 digits of pi from the Chudnovsky formula, you only need to sum about 70,000 terms. Compared to Madhava's 10 billion just for 10 digits, this is roughly 1 trillion times more efficient. And that's before any clever computer tricks even enter the picture. The story of how this formula came to exist is genuinely strange. David and Gregory Chudnovsky were Soviet-born mathematicians who emigrated to the United States in 1977. Gregory had a serious autoimmune disease that left him bedridden for most of his adult life. David built his life around taking care of him. They lived in a small apartment on the Upper West Side of Manhattan, and they did mathematics together. Gregory from his bed, David at the desk beside him. In the late 1980s, they decided they wanted to compute pi to a record number of digits. The problem was, no university would give them time on a supercomputer, so they built one themselves, in their apartment, out of mail-order parts. It was a parallel processor they nicknamed M0. It filled the living room. The cooling fans were so loud, the neighbors complained. They had to run extra power lines because the building's wiring couldn't handle it. In 1991, on this homemade machine, they computed pi to 2.16 billion digits. A world record. From an apartment. The formula they used, the formula they published in 1989, is what every record since then has been built on. Even today's 314 trillion digit calculation, running on million-dollar enterprise hardware, uses the exact same series the Chudnovskys wrote down on a notepad in their apartment. Here it is, the whole thing. 1 over pi equals 12, times the sum from k equals 0 to infinity of -1 to the k, times 6k factorial, times 545,140 plus 13,591,409k, all divided by 3k factorial, times k factorial cubed, times 640,320 to the power 3k plus 3 halves. I know, it looks like a monster, but the structure isn't actually that bad once you break it down. You've got a leading constant. You've got an alternating sign, that's the -1 to the k. You've got factorials in the numerator and the denominator that grow very fast in the same ratio. And then you've got a giant constant, 640,320, being raised to a power that grows with k. That last constant is the key. Every time k goes up by 1, the whole term gets divided by 640,320 cubed, which is about 262 billion, so term k plus 1 is roughly 262 billion times smaller than term k. Take the log of that ratio in base 10 and you get 14.18, which is exactly the number of new correct digits each term contributes. The convergence rate isn't an accident, it's baked into that one specific constant. To put that into perspective, the very first term of the series, just k equals 0, already gives you pi correct to about 14 decimal places. That's better than NASA needs to fly missions to Pluto. The second term gets you 28 digits, the third 42. By the time you've summed 7 or 8 terms by hand, you'd have enough digits to do calculations on the size of the observable universe to a precision smaller than a single atom. So where does that number come from? 640320. It looks completely random. It is not random. It comes from one of the deepest connections in number theory. There's a number called e to the pi root 163. If you compute it, you get something that looks almost like an integer. It's 262 billion.999999999 and then a few more nines before the illusion breaks. This near integer is sometimes called Ramanujan's constant, and the number 163 appearing in the exponent is what's called a Heegner number. There are only 9 Heegner numbers in existence. They come from a corner of algebraic number theory, involving imaginary quadratic fields and class numbers, and they have a magical property. They make certain modular forms produce values that are almost exactly integers. The Chudnovsky formula falls out of plugging the Heegner number 163 into a deep identity involving the modular J invariant and an Eisenstein series. The integer that almost equals e to the pi root 163 turns out to be precisely 640,320 cubed plus 744. So that strange looking constant in the denominator isn't a fudge factor, it's a fingerprint of a Heegner number. The reason the Chudnovsky series converges so fast is because it sits on top of one of the rarest, most special structures in all of number theory. Ramanujan glimpsed this in 1914 with the Heegner number 58, giving his famous series with 8 digits per term. The Chudnovskys realized they could push it harder by using 163, the largest Heegner number, squeezing out the maximum possible convergence rate that this entire family of formulas can ever produce. There's a real ceiling here, because there are only 9 Heegner numbers, and 163 is the largest. The Chudnovsky formula isn't just fast, it's mathematically the fastest a Ramanujan-style series can ever be. You cannot do better with this approach. Any future improvement has to come from an entirely different direction. 40 years on, no one has found one that wins in practice. So we have a beautiful formula. 14 digits per term. To get 1 trillion digits, we just sum about 70 billion terms and we're done. Right? Not exactly. There's a problem, a really big problem. When you're computing 1 trillion digits of pi, every single number in your calculation is a trillion digit number. That includes the factorials. That includes the powers. That includes the running sum. A trillion digit factorial doesn't fit in a regular computer variable. It barely fits on a regular computer's hard drive. And basic arithmetic, like multiplying 2 trillion digit numbers, using ordinary methods would take years. Multiplying 2 n-digit numbers the way you learnt in school takes n-squared operations. Multiply 2 trillion digit numbers naively, and you need a quintillion operations. Even a fast modern computer doing 1 billion operations per second would take 30 years for multiplication. So the Chudnovsky formula alone doesn't get you there. You need 2 more ideas, and both of them are computer science masterpieces in their own right. The first trick is called binary splitting. Here's the situation. You're trying to add up a long series, where each term is a giant rational number, a fraction with enormous integers on top and bottom. If you compute one term, then add the next, then add the next, you're doing tons of redundant work. Every addition forces you to find common denominators with these gigantic factorials. Binary splitting flips this. Instead of summing left to right, you split the sum down the middle. You compute the left half, you compute the right half, you combine them once at the end. The clever part is that each half has a structure where the numerators and denominators can be tracked symbolically. You never write out the full giant numbers until you absolutely have to. You build a balanced tree of partial computations, and at each node you do one big multiplication and one big addition. Because the work is balanced, the tree is roughly the same depth on both sides, the total cost drops dramatically. And because the tree structure is so regular, you can run different branches on different processors at the same time. Binary splitting parallelizes beautifully. The Chudnovsky's M0 machine and every modern Pi record computer relies on this. The result is that summing n terms of the Chudnovsky series doesn't take n times the cost of one term. It takes about m of n log squared n, where m of n is the cost of one big multiplication. The bottleneck shifts entirely onto how fast you can multiply two big numbers, which brings us to the second trick. If multiplication is the bottleneck, you'd better have the fastest multiplication algorithm humanity has ever found. And we do. It's called the FFT-based multiplication. The fast Fourier transform, the same algorithm that powers MP3 compression, JPEGs, MRI scans, and audio processing. It also multiplies giant numbers faster than anything else. The trick is that two long numbers can be thought of as polynomials. Multiplying polynomials is the same as convolving their coefficients, and convolution in normal space turns into ordinary multiplication in frequency space. So the FFT lets you multiply two n-digit numbers in roughly n log n operations instead of n squared. For a trillion digits, that's the difference between 30 years and a few seconds per multiplication. Modern implementations of Pi computation, like the program Y-Cruncher, which is what the new record uses, combine binary splitting on the Chudnovsky series with FFT-based multiplication, plus a final step called Newton's method to compute the reciprocal and the integer part of the result. The whole pipeline scales to nearly the theoretical minimum. This is what the December 2025 record actually does. It pours billions of dollars of compute hardware into a 1989 formula, multiplied with a 1965 algorithm, summed with a 1976 trick. None of the deep math is new. The Chudnovsky's choice of formula is still optimal. 4 decades later. You might wonder, surely someone has found a better formula by now. People have looked hard. There are other Ramanujan-style series. There are completely different methods like the AGM iteration, where each step doubles your number of correct digits. The Borwein brothers in the 1980s pushed AGM-based methods to incredible speed. Theoretically, AGM and similar methods should beat Chudnovsky asymptotically. They have lower theoretical complexity for very large n, but in practice, on real machines, they lose. The reason is memory. AGM works in steps where each step uses the entire current value of pi. So at step 30, you need to read and write a trillion digits, twice, just to do one step. The disk traffic destroys you. Chudnovsky, with binary splitting, has tiny intermediate quantities that fit in fast memory. The factorials and partial sums grow gradually. You only assemble the full huge number at the very end. So even though Chudnovsky theoretically does more arithmetic, the arithmetic it does is the kind modern hardware loves. Local, parallel, cache-friendly. The lesson is one of the most beautiful in computer science. The fastest algorithm in theory is rarely the fastest in practice, because real machines have memory hierarchies, parallelism, and cache. Chudnovsky wins not because the math is the most efficient possible, but because the math happens to align perfectly with how silicon actually works. So when the December 2025 record landed at 314 trillion digits, it wasn't a story about new mathematics. The math was almost 40 years old. The story was about everything around the math. Faster disks, more cores, better software, more electricity. The Chudnovsky formula was, and remains, the best tool for the job. A one-line equation, written down by two brothers in a Manhattan apartment, sitting on top of a rare connection between modular forms and a Heegner number from 1952, computed via a tree-shaped algorithm, from 1976, multiplied with an FFT trick from 1965, all working together to do the same thing humans have been doing since Archimedes, counting the digits of one specific number. There's something kind of wonderful about that. Pi doesn't change, the number is fixed. The hunt for its digits is in a sense completely useless. You'll never need 1 trillion digits of pi for anything practical. NASA uses about 15. But the chase has driven the development of half of modern computational mathematics. Every fast multiplication algorithm, every parallel computing technique, every numerical software package owes something to the centuries-long obsession with computing pi. So next time you see a headline about a new pi record, remember, buried under the press release is the same Chudnovsky formula, scribbled out in a noisy apartment in 1989, still doing the work no one has been able to beat. 3 centuries of progress, narrowing down to one perfect line of mathematics.